Hello everyone, so today we're going to be showing how the Maxwell-Stefan equations are expressed as a difference in component velocities is equivalent to the Maxwell-Stefan equations exposed as in terms of first the molar fluxes, which is Ni, and then to be the more diffusive flux, which is Ji. So to start, here is our first Maxwell-Stefan equation, and I first kind of want to run through about what everything means here, just so we're all clear about everything. So to start, our xi value is the molar function of a group. And actually, we're going to signify this with xa. Our next one is this gradient with that viscosity. But it doesn't actually mean viscosity. Here, it's the gradient of chemical potential of a species. So, our dig value is equal to, is a diffusion coefficient An important note to make here is that it's diffusing I into J here. So make a little note of that. And then our next value, we have the C value, is the overall concentration. Lastly, our N A's is equal to the molar flux of component A. So, to kind of talk us through this equation, we have the molar function of species I times the gradient of chemical potential of component I, all over the gas constant times temperature, and this is equal to the summation of the molar function of I times the molar flux of component J minus the molar function of component J times the molar flux of component I, all over the overall concentration times the diffusion coefficient of I diffusing into J. So, how do we relate that back to our molar fluxes? Well, first we're going to simplify this just a little bit, as this xi, our gradient of chemical potential, over RT, can be simplified to just this di value. So we're going to use that for a remainder, just for a little bit of simplification for easier writing. So our new equation is di equals the summation J equals 1 of the molar function of I times the molar flux of component J minus the molar function of J times the molar flux of component I over the overall concentration times the diffusion coefficient of I diffusing to J. So, when thinking about this, we have to consider the velocity Maxwell-Stefan equation. What Maxwell-Stefan equation is MSE. So this is equal to, di is equal to the summation of the molar function of a gas, yi, molar function of a gas of the J value, and that's times the difference of velocity of component J minus velocity of component I, all over the diffusion of I going to J. So, what are some key differences we see here? Well, first of all, we're missing this value right here, the overall concentration. So how do we get to that overall concentration to bring that back in? Well, to start, we can multiply top and bottom of this by this C value. So it's just we're multiplying by 1. So our new value is, well, actually, it's important that we understand this concept as well. So when we multiply concentration times, let's say y1, yi, we actually get the concentration of I because we're multiplying the molar function of this. So we're really just getting the concentration of component I instead. The same applies for J as well. So with that in mind, we can now add in or multiply in our C values, which gives us the following. So we have di is equal to J equals 1, and then we have Ci yi dj, then minus Ci yj di. That's all over C dij. So we actually can do some rearranging here and some simplification to further simplify this down. So an important concept to know is Ni is equal to Ci Vi. Concentration times our velocity is equal to our molar flux. So our flux is something moving at my velocity, and then additionally our concentration also has to be factored in here. Again, same rules apply for the J value, just so there's no confusion. So we have Cj and then J. So that leads us to the following. And then that y value staying there. So now, if we look back at what our old equation was, it's exactly the same. As we have those x values, but x and y are essentially the same. That's just in liquid form versus our gas form. So we related that back to velocity using these two rules of concentration being formed with the molar function of gas times our concentration of overall is equal to the concentration of the specific, and then times that, and then we also have another rule where we use the molar flux of a component is equal to the concentration of a particular component times the velocity of a particular component. So that is using the molar fluxes. So now let's go over the molar diffusive fluxes. So we'll put A right here, and we'll put B over here. So to start, let's call back to an important equation we used earlier today. So Ni is equal to Ji plus Yi times N. So using this equation right here, we can factor that back into our equation up here and then kind of create a bigger overall. So putting that back in, we get the following. The summation of this xi, our molar function, times that nj value. Again, same rule applies. Where we get Jg. So let's multiply that all out. There we get yij g plus yj and minus yj and gi yj yi on n. So looking at this, those two components cancel to where we get this. It's over C dij. So using this equation, we can realize that we're related already back to the same equation as we're using the more diffusive fluxes now as a j value instead of the n value. So there is part A and B of that, of the molar fluxes and the diffusive fluxes, relating back from our original Stefan Maxwell equation. Thank you very much. Hello everyone, today we're going to be dealing with, again, the Maxwell-Stefan equation and how it references with chemical potential as the pure state. So we're going to show that the Maxwell-Stefan equation is the driving force for a one-dimensional problem. It simplifies to just a derivative of the mole fraction with respect to the coordinate direction. So first of all, we're going to be dealing with the chemical potential here. And so in a pure state, this chemical potential is equal to chemical potential of a standard state. So just to write that out, so the standard states is marked by the 0 on the subset of it. So this chemical potential has two definitions that we use. So first, that we're going to use. So first is the chemical potential is equal to the chemical potential of the standard state plus RT ln of dui, xui. Another one is the gradient of this is equal to d chemical potential over dz, which will be in a reference to our position. So what is this and how can we simplify this? So first, we're going to put this into this equation, which would give us the following. We have D times our chemical potential at standard state plus RT ln of xi all over dz. And this simplifies into RT dxi, or excuse me, 1 over x I dxi over dz. So we can plug that back into this equation up here. So we have our xi, our molar component of xi, our chemical potential, which we just established is RT 1 over xi dxi over dz over rt. So these rt's cancels and these xi's cancel, giving us dxi over dz. So our equation ends up simplifying. We bring that back into this equation over here. This derivative of a mole fraction with respect to the coordinate direction, or dz, and that's equal to our Stefan Maxwell, which allows us to again translate this back into from binary conditions into multi-component conditions. So thank you very much. Hello everyone, so today we're going to be showing the Maxwell-Stefan equations, simplified Fick's law for an ideal binary mixture, and then also its relevance and application of the Maxwell-Stefan equation. So to start, we're going to be showing how this simplifies into Fick's law with an ideal binary mixture. So we're going to begin by putting this into terms for the molar differences fluxes. That's very important when we're dealing with the binary system. So we're replacing 1s and 2s. So I will be equal to 1, j will be equal to 2. That's a very important description we have to make here when we're dealing with Fick's law. So this dxi over dz will be simplified into d1 as di, and that's equal to d1. So from there, we can simplify this into our binary system, and we'll be using gas as well here because we're doing an ideal binary mixture, so we're going to assume that it's a low pressure gas. So we're going to assume this is gas. So this is equal to y1 j1 minus y1 j1 over c d11. So it's 1 diffusing into 1. And you may be thinking that's 0. That's correct. That's what we're looking for. We're going to add this together with y1 j2 minus y2 j1 over c d12. So this is obviously 0. And that gets us to the following. So d1 is equal to y1 j2 minus y2 j1 over c d12. So we're going to talk about some important concepts here to help us simplify here. So first, 0. So j1 plus j2 is equal to 0. And additionally, as we know from our y's, y2 is simply just 1 minus y1. So using these two definitions right here, we can actually plug this back into here and simplify this even further. So this d1 value is equal to y1 or j2, which again, we're going to simplify this j2 is just equal to negative j1 is equal to negative j1 minus y2, 1 minus y1, times j1 all over c d12. So again, let's try to multiply that all out. So we get negative j1 times y1 minus, so it's negative positive. We have negative j1 and then plus j1 y1 over c d12. So these obviously cancel out to where we get negative j1 over c d12. That's equal to d1. So this is starting to look pretty familiar. Is if we multiply that c d12 over to the other side, we multiply the c d12 to the other side, we have j1 is equal to negative d1 c d12. And then again, that's just equal, with d1 is equal to our dxi dz times c d12, giving us our Fick's law equation. So what is the application, the relevance to a Maxwell-Stefan equation? Well, take for example, we have a seven component system, right? There's so many combinations of interactions that happen within that system. As opposed to a binary system, it's very easy to do experiments and take data on them because you're only having one sort of interaction that's going on. So what the Maxwell-Stefan equations allow us to do is they allow us to take binary examples and then calculate the other sort of interactions that are going on within the system. So we can use Maxwell-Stefan as instead of doing hundreds of equations, we can do one or two and then calculate the other 98. So it helps us simplify and do a lot less data with do a lot more with a lot less data. So Maxwell-Stefan is used in a variety of different contexts and in a variety of different multi-component systems. So thank you very much.